So we have the problem to find the expression for pressure at a distance r from the axis, where a cylindrical container containing some liquid revolving around its principal axis with a constant angular velocity omega. Now, by looking into this problem, first question may be encountering in our mind that pressure is always depends on the depth, not on angular velocity. So how does angular velocity uh, come into play a role in the pressure? See, if we consider a cylindrical container containing some liquid, then we know that pressure at any depth h is defined by or given by the expression rho g h, where rho is the density of the liquid, g is the gravitational acceleration, and h is the depth from the open surface, right? Top, not from the bottom. Now, so the pressure depends on depth. How it is going to change while we are rotating this cylinder with an angular velocity omega? Yeah, it is correct that pressure is only depends on the depth. So depth from the open surface. Now as long as this open surface is remain flat, so everywhere, even if you move from the axis, it doesn't matter. If it is flat, then the depth near the axis or far from the axis will remain same. Now that's actually the breakthrough to this problem. So what will happen when we start rotating this cylinder with an angular speed omega? This open surface will not remain flat, because the angular speed will create a uh, cone like structure in the open surface, because the spin, due to the spin, it will create something like this. If you see the tornado or cyclone, so that is also the rotational motion of fluid. So when fluid start revolving about a central axis, it start creating a cone like structure like this. So this open surface will create some structure like this. So now the open surface is not a flat surface, so the height will gradually increase if we go far from the axis, right? If you go far from the axis, the height of the open surface will gradually increase like this. So that's how the expression of pressure is going to depend on omega, or we can say omega is constant for every point. Now it will be a function of r, because far we going from the axis, the height will be changing more. So let's dive into the problem and solve it step by step. So for that, let's move to the this part first. So I have shown here that a cylindrical container containing some liquid, it is not rotating. So initial step I am showing that 3 points, I have taken 3 different points, 1 to 3. So all are at the same depth h. So all the pressure P1, P2, P3 actually having the expression rho g h1, rho g h2 and rho g h3 respectively. Since the h1, h2, h3 are same, so this all P1, P2, P3 will be eventually the same. Now when we start rotating this cylinder with an angular speed omega, what will happen? This open surface of the cylinder will create a cone like this, right? So now the bottom of the cone, I can draw a flat horizontal line, and every point inside the liquid will be at same height from this horizontal surface. So this will be additional value of pressure. We are not worried about. So now suppose what will be the pressure at point 1. So if we see, the pressure at point 1 will be rho gh for this column of liquid, and additionally rho g y3, right, because this much height is above the h. So we can write the total pressure will be P equals to, if the atmospheric pressure P naught is at the open surface, then P naught plus we can say rho g y3 plus rho g h, right. This will be the total pressure at a point 1 or at the point 1, because the total depth from the open surface is rho g y3 plus h, and atmospheric pressure is P naught. So this will be the total pressure at point 1, right. So similarly at point 2 pressure will be, if we can write P2 will be our rho g h, or let me write it like P naught is the atmospheric pressure plus rho g h, or we can write first rho g y2 plus rho g h. This will be the total pressure at point 2, right. So this way pressure will differ at different point. So we have to express this y2 in terms of x2. What is x2? x2 is the distance from the axis, right. The far we are moving from the rotational axis, this y value will differ. So we have to express this y1, y2, y3 in terms of x1, x2, x3, the distance from the axis. So that is our primary task. If we can express in terms of if we can express y1, y2, y3 in terms of x1, x2, x3, then our work will be done. We will be done with this problem. So again, that must be somehow linked to the constant velocity, constant angular velocity omega. So let's see how we can do it. So to do so, I have taken here, I have drawn this open surface, and see at x3 distance the height is y3, right. So I have taken a point mass or a atom of the liquid, a molecule of the liquid. So on this molecule, or this particular molecule is rotating or lying at the top surface, open surface. It is revolving in a path of radius x3 about the axis. So the centrifugal force acting on this particle is mv square by x3. So now we can write, we know that v linear velocity is omega into r. Here r is the x3. So I have written m omega square x3 square divided by x3. So it will give us a value, that is, if we cancel out the x3 with x3 square, then we will get m omega square x3, right. And the mass of the particle, if the mass of the particle m, then mg is the force acting downward. So the resultant force of these two force is r. I am assuming that r is making an angle theta with the vertical. So to solve this, I have shown here clearly that our m omega square x3 is acting horizontally outward and mg is acting downward, so resultant making an angle theta with vertical. So here tan theta is our m omega square x3 divided by mg. So tan theta is nothing but dy by dx, right? So dy by dx is omega square x3 by g. Now we can write that dy equals to omega square g x3 dx, right? So we have written y value depending on x or r, that is the distance from the axis, rotational axis. Now we can integrate it for the whole value. So we can get any value y is equals to omega square g is the constant, so it is outside the integration, so omega square g is kept as it is. So what will be the limit? So we can integrate it from 0 to r is any value. So x3 dx, it will give us integration x3 square divided by 2, and if we put the value or limit as 0 to r, then we will get, by putting the upper limit, so we will get omega square r square divided by 2g, and lower limit will be 0, so it will be 0. So this is our y depending on r, right? So for pressure at any point P, which is actually r distance from the axis, we can write the expression that pressure P will be simply P naught plus rho g y, and if it is at any depth from the bottom of the cone, then we can keep an additional term as plus rho gh, right? Plus rho gh. So we can write again P naught plus rho g, and we can put the value of y here, so it will be omega square r square divided by 2g and plus rho gh. So here gg will be cancelled out, so gg will be cancelled out, and the expression for pressure will be P naught plus half of rho omega square r square by g, gg is cancelled out, so half rho omega square and r square, right? Omega square r square plus additional depth from the bottom of the cone, or it will be rho g h. So this will be the pressure at a depth of h from the bottom of the cone, which is revolving with omega angular velocity and at a distance r, right? So I can show this point as well. So I am indicating this point, let me draw it. So this is our tube or container, which is revolving with angular velocity omega about its principal axis, and while revolving it is making a cone in the top surface. So our h is the height from the bottom of the cone. So I have to draw a horizontal flat line at the bottom of the cone or the top surface which is making cone. So this is our H, this is my Y, right, and this is my open surface point P naught. So P naught is the atmospheric pressure at this point, and then there is a additional pressure. This term is for this value, this height is introducing this much, right. Let me use some other color so that, so this much height is introducing this much pressure, and this much, this height is introducing this much pressure, okay, this much rho gh, and this open surface pressure is this much. So the total pressure at this point, the depth is this much. Clear? So that's the expression. So let's remove all this and clear this. Right. So this is my expression of pressure. Okay, thank you.